All right. Howdy, everybody. Happy June. The summer oven is roaring here in Central Texas. I'm sure it is in any other part of the state you're in as well, but it's good to see you. I'm going to give it just a minute, let folks arrive. Feel free to introduce yourselves in the chat, just, your name and town or city you're coming in from. If you got a favorite swimming spot, I'm always curious about that. I just took a whole bunch of folks who'd never been to Barton Springs to Barton Springs Friday evening. I think they found God.
Excuse me, Dave, I can't hear you very well.
Oh, I'm sorry about that, Charles. Is anybody else having audio trouble with me? All right, Charles. Sounds like other folks are hearing me okay. I apologize about that. All right. Let me get the slide deck up on y'all's screen. Give me just a second to clean this up. Okie doke. Well, folks are going to be arriving bit by bit. Feel free to introduce yourselves in the chat. Drop any questions you have in the chat as well. My name is Dave Cortez. My pronouns are he and him. I'm based in South Austin. I'm the director of the Sierra Club Lone Star chapter, filling in for our water program coordinator, Evgenia Spears, who is just a couple skips down the road in Alaska for a couple weeks, having a vacation. Much needed after spending 6 months working her first ever legislative session at the Capitol. So much deserved, much earned vacation time. But we're going to talk a bit tonight about freshwater inflows with our esteemed guest, Dr. Audrey Douglas, and we'll hear more from her in just a moment. Let me go ahead and talk a bit here about our committee. So this is the Water for People in the Environment Committee is very much just a informal, casual network of advocates and activists who care about water, supply, quality, drinking water, wastewater, you name it, all different aspects of water from around the state of Texas. One of the main reasons we tried to build this committee was to help create a community of folks who have a broad range of different experiences around water issues. And a lot of times we point to common roads at either the Texas Water Development Board or the TCEQ, Texas Commission on Environmental Quality, and we end up with very common results, not always the pro environment results that we want. So we thought it would be important to build a network in space to connect people on that, but also share expert advice and perspective from folks like Audrey, who you're going to hear from tonight. Couple things to look out for this summer. You can see on your screen, we've got 3 great presentations coming up for our next few meetings. And, we do meet the second Monday of the month, every month at 6:30 on Zoom. And so we'll hear about the water energy nexus. Texas is building out a ton of power plants, whether you're in Central Texas, where there's definitely not enough water supply. We're seeing gas plants being built to provide cooling for data centers and other facilities, or Corpus Christi, where you're seeing a bunch of industrial facilities built and water supplies not really available. We'll hear about all those different connections from Dr. Margaret Cook at HARC. We'll also hear the following month more specifically about data centers from another HARC staff person, Dr. Aaron Kinney. And then in September, we'll hear more about coastal groundwater flooding from, and forgive me on the pronunciation here, Dr. Dorina Murgulet, who's gonna speak a bit about some of the issues in and around Corpus Christi. So I think you should be having the link to register for these in the chat. Again, welcome. If you just joined, feel free to introduce yourself, name and city or town in the chat. So a couple quick highlights, and forgive me, y'all, I was just the sort of behind the scenes person during the legislative session. Every now and then, I would show up to the Capitol and go talk to some very unfriendly people. But I got some great notes here from Evgenia, so I'm going to be looking off screen to pull from some of these. Water was a big deal this session. A lot of conversation, and as I've learned from our former director and water advocacy legend Ken Kramer, water's been a big issue at the legislature for over 50 years. All in all, water received $2.5 billion with an asterisk. About 880,000 of that 2.5 billion got carried over from last legislative session, which means that the next investment resulted from this session will be around 1.6 billion. But out of that 1.6 billion, about 580 million is locked in for very specific projects that different cities, counties, and other interests were lobbying for. So that leaves overall about $1 billion available for allocation by the Texas Water Development Board. You should receive an article linked in the chat from the Texas Tribune that gives some background on the funding that has happened there. The big water infrastructure bill was in the news a lot. Senate Bill 7 by Senator Charles Perry out of West Texas. He and others were pushing for what was called an 80-20 split. And we ended up, because of many of y'all's calls, organizing, and a broad range of people challenging that proposal, we end up with a 50-50 split, 50% to new water supplies in the State Water Infrastructure Fund, or SWIFT, and 50% to all other programs, as you see there on your screen. And forgive me, I was telling Audrey earlier, I getting over a cough here, so you might hear me cough a tiny bit from time to time. But the Texas Water Fund can now fund programs like agricultural water conservation programs, economically distressed areas programs like EDAP, or otherwise known as EDAP, potable water reuse projects, and the Flood Infrastructure Fund. Overall, we see this as a positive development, but in Texas, as you all know, we have to stay on the ball, keep our eyes on the ball, and keep organizing and attending meetings and advocating. We have to stay on top of the process and make sure that funding for flood control isn't going to diminish as a result of the Flood Infrastructure Fund being one of the many programs that will share that 50% of the 1 billion invested. There's going to be a lot of work at the Water Development Board and other agencies between now and next legislative session. Let me just briefly say, looking forward, we'll continue to keep an eye on this and meet with the Texas Water Development Board. And we very much welcome your participation and questions. Evgenia will be letting you all know about when we're having meetings, when there's opportunities for comment. I'll just say one last thing. So we're talking about $1 billion there, which will be recurring for water. The state of Texas gave out 300 million in grants to places, to aerospace industries, which is basically SpaceX and Jeff Bezos' operation out in West Texas. We gave out $5 billion to power plant energy companies to build gas power plants and some backup energy generating systems. We gave out several $100 million for nuclear power plant research and development, $8 billion for Operation Lone Star, and a whole lot. I don't have the specific number. Maybe y'all can chime in the chat for private school vouchers taken away from public schools. So we have to look at everything in context. This is a big win, but when it comes to the priorities of our state, we have to ask some tough questions. I do not see Dan. Are you on? Dan Mueller? Okay, Dan's not here, but let me go back real quick. You all will have a link in the chat to give you an article about produced water discharges in New Mexico. What might that mean for Texas? In New Mexico, um, the disposal discharge of produced water is now banned. And so it's a really interesting read to check out. Produced water, aka oil and gas wastewater. The state legislature and other oil and gas interests have been exploring ways to find other creative uses for very potentially toxic water supplies. So I'll leave that there for you all to read in the chat. And let me kick it over to Jason to give us a brief update on marine desalination.
Thanks, Dave. Hey, everyone. This is Jason from Corpus Christi. So over the last month, the Port of Corpus Christi Authority voted to abandon their inshore desalination permit. So inshore means it's discharging waste from desalination into the bay. And so this is really good news. Basically, they said that they're listening to the science, and that's why they chose to abandon the inshore permit. There is a caveat. They won't completely abandon it until they get their offshore permit, which they are working on right now. That's like a couple miles offshore. It's for 100 million gallons a day. But overall, it's a really good victory and a step in the right direction for desalination in Texas. And that's it for me. Thanks.
Shout out to Jason, Teresa, Peyton, Audrey, and anybody else from Corpus Christi and the Coastal Bend for y'all are an inspiration for the broad range of advocacy and work that you do. As someone from the desert who didn't get around water very much, it's really awesome to see and learn from you all every week. So with that, Audrey, you feel ready to go? Locked and ready?
Yep.
All right. I'm very grateful to introduce Dr. Audrey Douglas from Texas A&M Corpus Christi. I'm going to stop sharing. So Audrey, whenever you're ready, feel free to share your screen.
Oh. All right. And are you seeing the full presentation or presenter view?
Excuse me. I'm seeing the slide with a little note on the side. So I think maybe it's presenter view, but I can see it pretty clearly.
Still presenter view. Okay. Is the right one?
All right. Looks good.
This over here. All right. Thank you, Dave and Sierra Club, for inviting me to speak tonight. The title of my presentation is From Aquifer to Estuary, Groundwater and Surface Water in the Texas Coastal Systems. And there we go. I'd like to start first with a little disclaimer that any opinions, findings, conclusions, or recommendations I express tonight are my own, and they do not necessarily reflect those of my employers or funding sources. And I'd also like to acknowledge all of the graduate and undergraduate students that have been involved in the sample collection and processing over several years that have gone into the information, the data that will be presented tonight. I'd like to also acknowledge Dr. Dorina Merglet at the Center for Water Supply Studies. This is primarily her research here in the center. And I'd also like to acknowledge Dr. Paul Montagna at the Heart Research Institute. I worked with him in my postdoc on the book that I will mention on the next slide, but also the funding agencies that have that supported the work that's presented tonight. So I wanted to make sure that you're all aware of this resource. It's for the latest edition of Freshwater Inflows to Texas Bays and Estuaries. It just came out in January. It is an open access book, so with this link, you'll be able to access the entire book series. There's also an accompanying story map that goes with it that I would urge you to check out also. The book does get kind of into the weeds and very scientific at times. The story map boils it down a lot more into take-home points. And tonight I'm going to focus on one of my chapters from the book primarily, which is the groundwater surface interactions in the Texas coastal zone. So I'm going to start with an overview of the water cycle and freshwater inflows, and then also explain a little bit more about groundwater surface water interactions and its place in the water cycle and freshwater inflows. I'm then going to go into submarine groundwater discharge and subterranean estuaries, which may be new concepts to you. And then, if time, trends in global SGD and SGD studies in Texas. So this may look familiar to you. This is the traditional water cycle. It's a natural water cycle showing sources and sinks and transfer pathways. Nearly all surface water features like the streams, lakes, wetlands, and estuaries interact with groundwater, but that's not necessarily well shown here. You do have some arrows showing you have a seepage coming out, but it can also go in. You have recharge zones, water coming out into lakes and potentially back in as it goes under barrier islands, and then discharging also at the coast. This represents a balanced model where everything adds up equally or cancels out. However, this is a simple idealized system, and something important is missing, and that is human activities. So back, let's see, about 2-3 years ago, USGS released this new water cycle. They updated it, and this new water cycle better reflects the complexities of the water cycle by incorporating the humans into the picture through inclusion of common water uses like agriculture, industry, and even urban. So municipal use, urban runoff back into the system, domestic use. Other features that are included in this model as opposed to the simpler one, it differentiates more clearly between the pools and the fluxes. So all of the pools where water may be stored are in boxes. And then the fluxes are with the arrows. It also differentiates between freshwater, which is mostly what you're going to have in your terrestrial regions, and saltwater, your marine, and your transition zones. And then it also, and this is where, as a coastal hydrologist, I got excited, goes into expanding upon the complexities of the subsurface of groundwater. So it's not just a single layer anymore. You have confining units. You have confined aquifers or semi-confined aquifers. It shows that we sink our wells into multiple depths. So we're extracting from deeper aquifers as well as shallower aquifers. It also shows that we have freshwater, seawater, or saline water transition zones in the subsurface also. And a very important concept is it actually has a cone of depression. So here at the agriculture, they're pumping a lot of groundwater. And so the groundwater from the recharge area is flowing to the well, but you also have groundwater downstream or down gradient from that agricultural area being drawn back into those wells at this cone of depression. And this is pretty common and can have some negative impacts like subsidence. We see this up around Houston. Kingsville also has a pretty large cone of depression down there. So you can have, when you remove the water, the sediments can compact. And it's not just a simple matter of pumping water back in because the sediments have compacted. The water can't make its way back in easily and expand those spaces again. I'd also like to mention at this point in time that traditionally groundwater and surface water have been considered separately in resource management practices, though it is well understood that they're hydrologically connected, and development of one affects the quantity and quality of the other. So again, here, if you're pumping out a lot, you're potentially drawing groundwater supporting the stream away from that stream. An example of this here in Texas is that groundwater is considered privately owned. Under the rule of capture, landowners may capture and use groundwater beneath their property, while surface water is a public resource owned by the state, and the state grants rights to use the surface water for beneficial purposes. The separate management of interconnected resources is often problematic and can impede effective management of each resource. And again, my research has focused on those groundwater surface water interactions, particularly in the coastal zone. So these areas where you have seawater and terrestrial freshwater mixing. Just a quick reminder, the Earth's water supply. The Earth is called the blue planet because over 70% of the surface is covered in water. However, for all of that water, only 3% is fresh, and less than 1% is potable or drinkable. And even a much smaller percent is available in our streams and lakes. Most of it is tied up in ice caps and glaciers, or historically it has been. And then groundwater contributes 0.6%, so a little over 0.5% of the total water. And of the total fresh water, it's about 30%. So, but it's important to note that not all groundwater is fresh or potable. So groundwater can be saline, it can be fresh, but non-potable. It may have something dissolved in it that is not safe for human consumption. And most water use, over 70% worldwide, is for agriculture. There are different types of streams. So we have gaining streams, we have losing streams. Rivers and streams are strongly influenced by groundwater. Depending on the relative elevations of the water table, which is this dashed line here, and the surface water levels, you can have a gaining stream. So that's where your water table is higher than your surface water level. Or if that water table drops below the surface water level, you have a losing stream. So the surface water is actually recharging to the groundwater rather than being groundwater supported. And some streams, some rivers may be perennially, or over the course of a year, they're pretty much always a gaining stream. Others may be intermittent, depending on if it's a wet season or a dry season. It may shift back and forth. And then others may be ephemeral streams, where they pretty much only have stream flow in like a major flood event or immediately following precipitation. This concept is really important for understanding drought or understanding what we're seeing right now in Texas. So right now we're in the middle of a hydrologic drought where a deficiency in the water supply in our rivers, lakes, and groundwater have resulted from prolonged periods of precipitation shortfalls. So this is primarily driven by meteorological drought or our weather patterns. So we've had many dry years and not enough wet years. So we have an ongoing deficiency. If you go up to our reservoirs right now and you see that water level, those white lines, where you can see where the water level used to be and where it is now, that current water level is basically the water table. So that is, we don't have groundwater sufficient to be recharging our surface water and bringing those water levels up. Another impact, or something else that has impacted freshwater inflows, is dam construction or reservoirs impoundments. So since the 1960s, the amount of water in reservoirs has quadrupled. Withdrawals from rivers and lakes has also doubled. This has increased threats to humans and the environment through increased occurrence of flooding and loss of buffering from extreme events due to habitat loss. And also people increasingly occupy regions like the coast that are exposed to extreme events like tropical cyclones. So there's also been an increase in intercepted continental runoff. This is 3 to 6 times as much as the water in reservoirs as in natural rivers. So freshwater inflow has an indirect effect on biological resources. Studies conducted in Texas over the last 20 to 30 years have led to an approach to study freshwater inflows and the creation of inflow standards. The domino theory shown here is a conceptual model that explains how freshwater inflows indirectly affect estuarine resources through estuarine conditions. So in this model, you have the freshwater inflows affect the estuarine conditions, which then set what's needed, what's necessary for estuarine resources. So the freshwater inflow is largely controlled by the quantity, so how much is coming in, which is impacted by the timing, the frequency, duration, and extent. So how long is it coming in? How often is it coming in? What time of year is it coming in? And then is it just a single watershed? Is it, the entire Texas coast was under a cloud? And, it was everywhere. Also, the quality and the tidal connections are important here. So for estuarine conditions, the freshwater inflow is impacting the salinity. Where you have more inflow, you'll have lower salinity. Where you have less inflow, you'll have higher salinity. It also impacts the sediment. So how much sediment is coming in, how far that sediment gets carried into the estuary. And it impacts the dissolved materials or the solutes. We often refer to these or focus on the nutrients or the inorganic nutrients like nitrogen and phosphorus. And then also particulate material. And this isn't the same as sediment. This is, you have branches, twigs, leaves, and other particulate matter, including shells, that can be transported. And again, these estuarine conditions then create the habitat that determine where the estuarine resources are and what type, so the integrity, function, and sustainability. There's a component missing from this conceptual model, and that is climate. The climate actually is a big driver, or the biggest driver, of freshwater inflows. Again, if you have that meteorological drought, it's a dry year or it's a dry period, you're not going to have as much freshwater inflow. It's going to be diminished. So again, important part to include or to consider in this model is that climate drives freshwater inflows, which drives the estuarine conditions, which create habitat and drive the estuarine resources. Senate Bill 3 in 2007 generally follows this model of the inflows, estuarine conditions, resources as an ecosystem-based approach. The previous House Bill 2 in 1985 instead did a species-based approach, which went straight from inflows to estuarine resources. It didn't have this center component. So this is the evolution of the idea of the domino theory. Where precipitation happens matters. The annual precipitation average in Texas. So Texas has a strong east-west precipitation gradient. We get a lot more rainfall in eastern Texas than we do western Texas or even southern Texas. And this gradient is captured along the coast. The Gulf Coast aquifer underlies the Gulf Coast, so you can see that right here in gray. And the aquifer is actually thicker in the northern portion and thinner in the southern portion. But the GCA is described as a leaky artesian aquifer. This means that the different aquifer units, so the Chico, Evangeline, and Jasper, are separated by semi-permeable layers rather than impermeable layers, or at least the Chico and Evangeline are. So this means that they're not, fully confined. There could be migration of water across between them. The aquifer outcrops are inland, so where the aquifers come to the surface. This is going to be where the most recharge is, especially for those deeper aquifers. And for the Gulf Coast aquifer, that's generally going to be, around here. So the hill country for us. So as I said, it matters where the precipitation falls. For the aquifers to be recharged, we actually want it to rain in San Antonio. We want the bulk of the rain to happen up in the hill country to support the down gradient aquifer. That rain up in the hill country supports our streams. So long term, that's where we want it to rain. I'm not saying, we don't want rain here. We need it also, but we'll do much better if the bulk of it is occurring up in the outcrop and recharge areas. So the inflow gradient, because we have this precipitation gradient, we also have an inflow gradient. So it makes sense that where it's wetter in the east or northeast, you'll have more inflow. And then as you follow the coast south, you get less inflow. So our more northern estuaries or northeastern estuaries are going to have a positive inflow balance. So this means that the inflows exceed evaporation and outflows. Whereas our more central coastal bend estuaries, Mission Aransas and Nueces, are neutral. They balance out over time. And then Laguna Madre is a negative estuary. You have a lot more evaporation than you do inflows. So recognition of the importance of submarine groundwater discharge continues to grow. This was using these search terms in the Web of Science. I looked up how many studies have been published. And since submarine springs were identified as a neglected phenomenon of coastal hydrology back in 1996, the related fields of study have grown tremendously. So you can see, and I fully expect by the end of this decade that this will be, way up here. I don't know if it'll continue at an almost exponential rate, but it will continue to grow. Because already just in the first 2 years of this decade, the number of publications exceeded those in the aughts. In total, there have been almost 5,300 unique publications, of which only 21 studies were conducted in Texas. And all of those were in 3 estuary systems at the time. And that was Upper Laguna Madre, Nueces Estuary, and Mission Aransas. So it had all been confined to the coastal bend. There are now studies being conducted up in Matagorda, and I think Galveston also. So what is submarine groundwater discharge, or SGD? You will hear me say SGD a lot tonight. And SGD is any flow of water on coastal margins across the sediment water interface, irrespective of its composition, origin, or driving force. A lot of words. What does that mean? Means it's water coming out of the sediments into the surface water above it, and it can be fresh, brackish, saline. It can be of terrestrial origin, so coming from that groundwater up gradient, or it can be oceanic. So think of the tides pushing in and pulling out. That is also SGD. It can be driven by wind waves, density, bioturbation. So there's a lot of mechanisms. It's not as obvious as river discharge in many locations. It's more of a diffusive process than an advective process. But continental groundwaters are discharging directly into the sea as submarine groundwater discharge, just like rivers are discharging at the surface. And this occurs wherever there's a hydrologic connection between the aquifers and the seafloor. SGD is an important component of the global hydrologic and biogeochemical cycles that link terrestrial waters to marine environments. And I also want to make a point of clarification here, because I may use them interchangeably. But where sediments are saturated, like in our rivers, in our bays, offshore, so as we would expect in any submerged materials, groundwater is synonymous with pore water. So the distinction that I generally make is groundwater is under dry land, pore water is under water bodies, in the sediment, but under water bodies. And see if I can get it to play. So these are pictures from the Yucatan, from a trip we did down there that show very strong advective groundwater discharge. So you can see right here, at the surface, the impact of the groundwater coming out, and here. And then these are underwater photos of springs where they're coming out. So let's see if I can get the video to play. There we go. So this is one of the larger springs off the Yucatan. I think it's off Zalam de Bravo. So then you can see water where it's not coming out. As I said, there's many mechanisms that drive SGD. Some of them occur at large scale processes. These are meters to kilometers. And then others at small scale processes, micrometers to meters. Generally, the ones that we talk about most or think about most are our terrestrial hydraulic gradient. Again, what is our inland water table? And what is that, height difference between that water table and sea level? And then that freshwater seawater interface. There's fluctuations in the water table based off of if it's a wet season or a dry season. So those fluctuations, and that also will shift that freshwater seawater interface seasonally. We also have wave setup or tidal pumping. So at low tide, your surface level is going to be lower than your water table, so you'll have more flux out. At high tide, it may be higher than your water table, so you'll actually be pushing water in, and it'll be seawater intrusion, at least temporarily. So this is kind of a round and round circle. Also, one that needs to be considered here on the Texas coast is water levels across barriers. We do have our barrier island system. So if there is a difference in water level in our lagoons and bays compared to the Gulf, that can create flow through the barrier islands, one direction or the other. We don't have a strong tidal cycle in the Gulf. We're microtidal. So we generally see this more when we have storm surge, whether that's positive or negative. And then there's small scale processes. And the main thing is that the interactions between groundwater and surface water occur at a range of spatial and temporal scales with highly variable magnitudes that depend again on weather patterns, the riverine activity, water movement, geologic processes and settings, as well as human impacts. When we're measuring SGD, there's a variety of techniques that can be used, elemental and isotopic geochemistry. So we can use naturally occurring radioisotopes like radon or the radium quartet, particularly in areas that have uranium and thorium deposits. This is a really good one because the source is going to be sediment. You can also use stable isotopes of oxygen and hydrogen or trace metals. There's modeling of groundwater flow, so Darcy's law, which is a very important one in hydrogeology. You have density-dependent flow, transportation, direct measurement by seepage meters. There's different geophysical techniques and thermal imaging. Each of these methods has its advantages and its shortcomings. For example, the direct measurement by seepage meter is just a point measurement. And so it tells you what that discharge is at that point, doesn't tell you about the rest of the area. In contrast, radon and radium are an integrated signal. So it's from that area around it, it discharges and it mixes and you're getting that integrated signal. So the best studies really use multiple complementary methods to attempt to address the drawbacks and fill in the blanks. So the next concept I want to go into is the subterranean estuary. So this is kind of an as above, so below. This is analogous to the definition for surface estuaries as a body of water where seawater is measurably diluted by freshwater inflows such as rivers. Billy Moore in 1999 coined the term, and he defined it as a coastal aquifer where groundwater from land drainage measurably dilutes seawater that has invaded the aquifer through a free connection to the sea. This was more recently updated by Duke et al. As the part of the coastal aquifer that interacts actively with the ocean. So it needs to have an active exchange, active interaction going on, and includes all the relative physical, chemical, and biological aspects that excite researchers working at the land-sea intersection. And really, this was an attempt to bridge different fields. So you have hydrogeologists that are like the land to the ocean, to the coast, and don't really go offshore too much. Then you have oceanographers and marine scientists that are from the coast offshore, and really a lot of them aren't even going up to the waterline at the coast. So the subterranean estuary is an attempt to bridge and look at it in terms of there's a coastal zone, there's interactions back and forth that are important to look at. So where does the subterranean estuary fall? It's right here. So we have our, more traditional estuary where you're diluting seawater with riverine inflows. And then you go below the surface and it's going to be similar. So you have surface and groundwater, estuarine, marine, subterranean estuarine. STEs are an important concept to consider because they are biogeochemically active. This slide is a lot, and my main point with this is that just understand that there's a lot of chemical reactions taking place depending on how much oxygen is present. So we have the oxidation reduction ladder, if you remember that from chemistry, very strong here. So where you have oxygen in this oxic layers, nitrogen is going to stay as nitrate and phosphorus is going to primarily stay particle bound. But as you consume the oxygen and move down and deeper into the sediment, or just as down the redox ladder, then nitrogen may convert to ammonium and phosphorus may be released from those the particles, the sediment. So there's a lot going on, a lot of different processes that control what is coming out with the groundwater that's discharging. So I'll go through this last part pretty quickly, but global trends for SGD inputs, can see that it's, a coastal phenomenon primarily, with how we discuss it. And it's generally highest towards the equator. And we don't actually have information in the Arctic and Antarctic. But also, if you look over here at the river discharge is also highest towards the equator. And so it kind of follows along with those trends. And that follows a lot of our global scale cycles for where precipitation occurs. So fresh SGD also varies. And actually, this is based off of modeling, not necessarily measurements, but taking literature from around the world and modeling it. But fresh SGD accounts for less than 1% of total freshwater input, but 2% of solute input for carbon, nitrogen, silicate, and strontium to the oceans. So while SGD may be volumetrically less than surface water inflows, it's proportionally more important for solute fluxes and nutrient cycling. So for studies in Texas, as I said, it's primarily focused on 3 estuaries in the coastal bend. And what we have seen is that submarine groundwater discharge is actually orders of magnitude greater in Corpus Christi Bay, which doesn't make sense. And I have to say, when I present, or shouldn't make sense, and when I present this at conferences, we get a lot of people giving us funny looks. So we had to do, think outside of the box and do some deep diving into why Nueces Estuary, like what makes it different from the others. And part of that is, you can see these kind of reddish brown lines. Those are growth faults in the area that transect the bay. And those growth faults potentially serve as conduits for enhanced groundwater discharge. So groundwater from deeper aquifers can potentially follow those faults up to the surface. So that's one possibility. I also want to say that in the Nueces Bay, this chunk here was my dissertation. So again, we have the growth faults. In my dissertation, it was a 2-year study. We collected surface pore water and groundwater, 3 different estimates for groundwater, for SGD fluxes rather. And then we did a follow-up survey using mobile continuous radon and continuous resistivity. And the track for that follows this purple line here. Over the course of this study, we actually started in a drought period. So this is the salinity in Nueces Bay. And the 05, the black line, is in the river. And then we have blue is in the middle of the bay. And then red is in the western portion of the bay. So we can see that it was hypersaline. The salinity was above 34, 35. I think it was close to, it was like 39. So it's higher than seawater. That means it's a inverse estuary at that point in time. And then we had a major precipitation, very wet spring, lots of flooding, and look at those salinities drop. So we captured some interesting conditions, drought, flooding, and then recovery to more normal conditions. So this is what the saltwater barrier dam at Cal Allen looks like at the beginning during the drought, and then after the wet period. So these saltwater barrier dams, depending on which river they're on and where they are on the coast, may serve as a barrier for flow reaching the estuaries. And this contributes to the bay becoming hypersaline during that drought period. So the SGD trends that we saw It was highest in the river pretty consistently, which makes sense. Parts of the river, or at least the part of the river that we were sampling, was groundwater supported. And then looking at the activity ratios of the radium, and really quickly here, so radium, there's a quartet, there's 4 different isotopes. They have different half-lives, ranging from 3.5 days to 1,600 years. So the 224 here is 3.5 days, the 226 is 1,600 years. So looking at the ratios of the short-lived to the long-lived, it can start to interpret processes that are going on. And the key takeaway here is that we had activity ratios greater than 1, which followed more along shallow groundwater signatures, but we also had activity ratios less than 1 that follow the deep groundwater signature. And then overall with our comparisons with the Darcy estimate, we had a large range of potential groundwater discharge from 0.02 to 8.2 meters per day. And 8.2 meters per day is a lot. So think of it as like a horizontal. If you had a hose at one end and you started letting water flow out, that water is traveling 8.2 meters in a day. That is how far the groundwater is moving, or that is how much is coming out, if that kind of helps you conceptualize that. In the literature, this is unheard of in systems like ours that have a lot of clay and fine particles. So this, again, we were like, what is going on? The radium or the saline SGD was more what we would expect, 0.01 to 0.03. And that also matched the previous study, or was closer to a previous study in the literature. And then our radon, which is a total, it was kind of closer to the range from the Darcy, but not quite as large. So, and our most conservative estimates there were more realistic for what you see in the literature. But again, you know, we get funny looks when we present this at conferences. So,
well, Audrey, I'm going to interject for a moment. This is, if you're getting funny looks from me, it's just because this is my first time hearing it all, and I'm learning so much. So thank you. And I think I'm seeing from some other folks in the chat the same thing. We've got about 5 minutes to go, so I wanted to give you a chance to tie it all together and see if there's any questions.
Okay. So this is a good figure for kind of summing up what's going on in Nueces Bay. And I'll go to the next one first. Nueces Estuary has had a lot of oil and gas exploration, particularly up in this White Points location. And each of these wells that gets drilled is a potential short-circuiting of a confining layer. And what short-circuiting means is that you can then you've created a connection between previously separated aquifers. So since it's an artesian aquifer, it's under pressure, so that connection generally is going to be an upward migration. So with all of these wells that have been drilled in the area, we've potentially enhanced groundwater discharge from deeper groundwater. That could explain why we're seeing deep groundwater signatures in wet years. We've also got in the middle of the bay, it's very muddy. When we put our pore water sampler in, if we let it go, it just keeps sinking and sinking and sinking down to 3 to 4 meters into the sediment. That is an indication that there is an upward migration, continuous upward migration of groundwater that's keeping that fine particle fluffy and suspended. So the disturbances in Nueces Bay may be contributing, and throughout Nueces Estuary, as well as the growth faults, may be contributing to why we see such high SGD rates compared to other systems. In our continuous survey, we saw that groundwater peaked, or SGD peaked, at the kind of edges where you're transitioning from those fine-grained clays to sandier. Something we would also expect to see because water is going to flow better through sandier than through clay. And that's a picture of what we see in the middle of the bay. I'll skip that one. So quickly with this one, bringing it back to the nutrients and the nutrient fluxes from groundwater and what's coming in. We did a principal component analysis. This is a method used to simplify complex data. So it takes a large set of related variables and reduces them to a smaller set of new variables that we call principal components. And in our analysis, combined, they explain about 56, 57% of the variance in the data set, so of the differences. And our first component is freshwater inflows. And we can identify that as freshwater inflows because we have salinity with an opposite or inverse relationship to temperature, as well as silica, phosphate, and dissolved organic carbon, which we know are terrestrially sourced, get higher concentrations closer to the river mouth. So where you have low salinity, you're high in those. Our next component was actually recirculated or recycled nitrogen or old nitrogen. And we see that here where we have our reduced nitrogen, ammonium, dissolved organic nitrogen, going with our activity ratios and opposite of pH. And then we have the total SGD or oxic nitrogen as our third component. We have the oxygenated nitrogen or NOx with radon there. So conceptually, what does that look like? You have your new nitrogen from your more terrestrial sources coming in. That's going to be more oxic. And then you have that recirculated component, which in this system is smaller, but that's giving you old nitrogen. Quickly with this, I just want to touch on the SGD-derived nutrients. Why do we care? We care because they support the base of our food web in marine systems. So these nutrients are needed by phytoplankton. They take up the nitrogen, phosphorus, silica, whichever they need most. And so if you have a large influx of nutrients from groundwater, potentially that can lead to a harmful algal bloom or other negative as well as positive. It could support your the base of your food web and bring in more fish that it's feeding, supporting your estuary. It's about finding a balance there. And in our system, we do have a lot of silica and nitrogen-rich samples. The last thing I'd like to touch on is that, as I mentioned earlier, groundwater and surface water are managed separately. We don't currently have a framework that incorporates SGD into decision-making. So there's a link, hopefully, that's getting shared to this paper that provides an example of a framework that could be used or could be applied towards incorporating SGD into a decision-making framework. This focuses on ecosystem services, and the goal is to achieve coastal society well-being, which is defined as the capacity of an ecosystem to provide the conditions for physical, social, psychological, and spiritual fulfillment through balancing synergies and trade-offs. And an example that the paper gives here is a coastal community decides fresh SGD is a resource to be collected and consumed. So what are the synergies within that? You are supporting, or that SGD supports water cycle, nutrient cycling, and habitat. It's provisioning, or through supporting, it's creating fresh water and food for us. It also has regulating impacts for biological control, and through food, it can impact cultural heritage. Think of our shrimpers and fishers on the coast. But there are trade-offs. So you may be sacrificing nutrient cycling and habitat that in fact that impacts provisioning. So you may be sacrificing food there too. If you lose that habitat, you may be losing your biological controls, and you may be losing your cultural heritage. So it's just an example of a framework, but it's something that we need. So I just have a few key takeaways. So groundwater, surface water are interconnected systems, but are managed as separate systems. Groundwater is a neglected component of freshwater inflows. SGD may be smaller volumetrically than river inflows, but may have substantially greater impact on nutrient cycling. STEs are biogeochemical reactors where terrestrial groundwater and intruding seawater mix and interact. And we need a framework for incorporating groundwater and SGD into our freshwater inflow and water resource management decisions. So, sorry I went long.
You're good. You're good. Thank you. I think I mean that was an amazing course. I really appreciate all that breakdown. Feel free to stop the screen share, y'all. I know we're a little past time, but we can stay on for a couple minutes. There's some questions that have been in the chat and some praise for you as well, Audrey. Thank you. There was a comment from Darshana. You know, what is as a citizen, what actions can we take besides reaching out to our lawmakers? First, I'll say, and then I'll open it up to you, Audrey, and Jason, and Peyton from the committee. Teaching people, sharing and learning together is a huge, important step. Before we talk to lawmakers, before we talk to, you know, administrative officials at the water utility or the water development board, the more that we can learn about these issues and how it connects our communities is always a good thing. But being part of this committee is another good thing, because this is what we do. We try to help each other learn, and we try to connect each other to a range of advocacy opportunities. So Audrey, anything else you'd like to add to that, or any other members of the committee?
Education is a big one. It can be a struggle to take these complex systems and processes and boil them down into a soundbite or a bite-sized piece. But you know, through education and understanding the systems, we can, you know, have more informed conversations with our lawmakers, with our legislators. For example, my opinion and perspective on desal has changed drastically from a heck no, we shouldn't do it, to a we're at a point where we have to do it, but it needs to be done right. And so that is with the offshore component. And the reason we have to do it is because our coastal population is still growing. And we are in a hydrologic drought, and a hydrologic drought we won't recover from for many, many years, if ever, because we continue to exacerbate it through extraction. So education, you know, attending these meetings and then sharing what you've learned, sharing the presentations or recordings, and talking about it, not being afraid to talk about it. I also teach federal environmental laws and regs, and a lot of my students shy away from talking about it because it's inherently political, but you know.
Yeah. Well, you're welcome to send them our way. We're a mix of nerds and politicos, organizers, you know, you name it. I see a question here from Tom. Is the quote unquote zone of bad water in the Edwards Aquifer considered to be a subterranean estuary?
Zone of bad water. Oops.
Tom, do you want to say a little more? Maybe you can clarify.
So in the Edwards Aquifer, it's not going to be a subterranean estuary because you don't have the mixing with surface water. It's going to be part of the aquifer.
Yeah, in the Edwards, the inland portion of the aquifer is fresh, and as you get closer to the coast, it's saline, and what they call the zone of bad water is where the two are mixing. And I think it's pretty well in from the coast. That's why I asked the question. I'm not sure if it's considered in that category, but it's definitely where the transition from freshwater to saltwater occurs, and people worry about if that moves very far inland, it may mean that you have saline water in people's wells.
Yeah, that is a concern. With the updated definition for a subterranean estuary, I don't think it counts because you don't have active exchange occurring. So I think that's just going to be the transition to saline groundwater. And it is concerning that we do have that transition zone slowly creeping inland. Because recharge has decreased and we're pumping out of our aquifers. Because if you think about it, that aquifer matrix, all of the rocks and that salt water comes in contact with, chemical reactions are occurring. Things are coming out of the water or coming into the water. And as that water retreats at some point in future, you now have aquifer material that is not what it was when it was fresh. So you have potential for contamination of freshwater resources through prior saltwater intrusion.
Thank you. Let's take one more, just because we're getting towards the end. And you all, you're welcome to drop any other questions in the chat or email them. I'll put my email in the chat along with Evgenia's, and we'll follow up. But the last question here will be, how does the proposal to use aquifers for water storage affect salination?
That is going to depend on the water that is being injected. If you have fresh water being injected, it's going to decrease the salinity or keep the salinity low. If you're injecting brines, you're going to be raising your salinity.
Awesome. There's more good stuff here in the chat. I'm so sorry to cut us. We're 10 minutes over. I've got a little one.
Sorry about that.
I'm pretty sure. Oh no, we're good. Pretty sure all the bath water is spilling out. Thank you all so much for joining the Water for People and the Environment Committee this month. Again, we'll meet in July every month on the second Monday of the month. Shout out to Jason and Peyton for helping with the links and support today. And again, round of applause for Dr. Audrey Douglas. I'm actually excited to go back and watch this recording. I'm going to need another go at that. So thank you so much.
And I'll add my email to the title slide and share the presentation. You can share it. If you have any follow-up questions, please feel free to reach out.
Awesome. Awesome. Thank you. And there's some more links there in the chat, you all. You all stay cool and have a good summer. We'll see you next month. Bye, y'all.
Bye.